Okay, y'all, so this wouldn't be a Will presentation if I didn't screw up and say this is the last video and then have another one after it. So here's the last video. So we're concerned with how concatenation and truncation interact. So we're going to break it down into two cases, mainly when n is, obviously when the number is greater than 0, it is a concatenation with a finite 0 string, and when it is less than 0, it is a truncation of the first m terms. So first, if we're going to be concatenating first and then truncating, so n happens before m, n greater than 0, m less than 0, then what we're going to get is that that's equivalent to this here, and we can split that up into two cases, namely when the magnitude of m, because remember m is negative, so negative m is going to be magnitude. So when the magnitude of m is less than n, and when the magnitude of m is greater than n. And what we're going to see is that this is just the same thing as u plus n plus m. And the reason being is in the case where the magnitude of n is greater, you're going to add n zeros to the front of a string, and then you're going to truncate m of them, which is less than the number of zeros there. So you end up not touching the original string, and the number of zeros left is going to be the difference in magnitude between the two numbers, which is going to be positive. So you're going to have u plus of n plus m. In the case where the magnitude of m is greater than n, you're going to add n zeros to the front of your sequence, and then you're going to truncate all n of them, plus you're going to truncate more. You're going to truncate m plus n more terms, so you're going to end up actually affecting the original sequence and not just having, you're going to truncate part of the original sequence. So in the end result, you're still going to have u plus of n plus m, it's just going to be negative in this case. So because of the analysis that we did in the last video, we get that that J acts as a homomorphism in this case as well. So all that we have left to do is show when the truncation happens first. So here n is less than 0, is greater than or equal to m. So m is going to be the positive one, so it's the concatenation with a finite 0 string, and n is going to be the truncation, in which we're doing first. So what we're going to get here is that the dimension of the kernel of mn is equal to the dimension of the kernel of join negative n. And the reason being is that we've truncated first. So the first n terms of your sequence that you start with disappear. And then there's no getting them back. We've already truncated them. All m is doing here is going to add on zeros to the front. So you've lost information, which means that the size of my kernel is going to be the same as that of u negative n, u plus star negative n, because it's going to be the same amount of information lost as a truncation. The two functions are not equivalent because you've concatenated zeros in the front, but concatenating zeros does not add anything to the kernel. So the kernel is just going to be the same as for u plus star negative n. Secondly, if we consider the adjoin of this function, we're going to get that the dimension of the kernel of the adjoin is the same thing as this guy here, the dimension of the kernel of this guy here, just by basic manipulation of adjoin over a product. So what we get here is that m is happening first, but more specifically it's the adjoin of m. And because n was negative, this negative n is going to be positive. So what this guy here is doing is truncating the first m terms and then concatenating on an n-length finite string of zeros. So the amount of information that's being lost, the number of dimensions that are falling to the kernel, is going to be the same as that of u star m. So we're just going to get m for the dimension of the kernel of this guy as well. But this is the adjoin of this guy, which means that if I ask for j of this one, it's just going to be this value minus this value. And I apologize, that should be, this should be a negative n. I apologize. So we get negative n here, right? Because n is negative here, so the dimension should be a positive number. So we're going to get this guy minus this guy, which is negative n minus n, which means that we get that is a homomorphism in the final case as well. So for all cases, we have that J is acting as a homomorphism from our Fedhelm Fedhelm operators onto Z. So this is in fact going to be the show that these unilateral shifts are in fact, the generalized unilateral shifts are in fact the representatives for the abstract index group as desired, and that they are also then the representatives for the classical index group because they are imitating Z. So that's it. Hope you guys have a great summer. Hope you enjoyed this last round of lectures, and I will see you guys in the fall.